So, you can check this section because with this course, it says it has two sections, and this is one, and then this is another one.
This is online section. I don't think I have online section.
And currently there's 50% enrolled in
Huh?
it. So that's what I was a bit confused about. And some students were waiting on when the course will show.
Oh, okay. Let me see. So there's an online section.
Yeah,
So 50 students enrolled on the online section.
yeah,
But I didn't see anything on my side.
yeah. So yeah, there's kind of two sections
Uh-huh.
it shows up. And usually I know the way of this.
Can I take a picture of
Yeah,
this and I will ask the department coordinator.
And I can also take a picture of this to show.
I will ask the coordinator. Oh, thank you. Okay, let's start today's topic, democratizing AI. I will talk about in today's class. I will talk about like those special topic on democratizing AI. I will like this presentation is from efficient large AI models to network compression theory. So basically, our efficient AI have some algorithms, have some practical applications, and also have some theory to support the efficient AI algorithms. So we will have a easy to hard mode. Like initially, we'll talk about the more practical side, and at the end of the presentation, we'll talking about some theory part. So basically, within recent maybe not several years, just a couple of years, we have witnessed very rapid growth of AI models, right? Those very cool models. Like the first example on the left side is the large language model for coding. Like we can use the human language as a prompt, and correspondingly the large language model can generate the code in programming language. Right? This is a very big breakthrough in the natural language processing domain. Like I think 5 years ago, now like a NLP researcher can imagine that we can use the machine learning algorithms to generate code. Like in the year of 2025, all the thing is doable. So it's because of the capability in the large language models. And the second demo is on the right side is the vision generating model powered by the diffusion model. Basically, as the input is similar, we can input some human language as a prompt for the vision generating models, and correspondingly, the diffusion model, the vision generating model, can generate very instruction following, very high resolution, realistic, temporal consistent vision outputs like those high quality images and high quality long sequence videos. They all can be generated by the diffusion models, right? This is basically a very big breakthrough in the computer vision domain. So within recent 2 years, we can say we can witness those two big breakthrough in our like AI domains, like the computer vision, like the natural language processing. Like, but does anybody has any idea about what's the potential computational cost? What's the pyramids? Like because we know that it's large language model is large scale vision generating model. But does anybody has some brief idea what's approximately pyramid size of those two models?
33 billion to like one of them.
Yes, yes.
43 billion for consumer GPU.
Yeah, the answer is quite surprising. For generating the coding, you need the large language model to have around at least 400 billion parameters. So basically you cannot run the code generation model on your customer user GPUs. That's why I think Cloud Code and Cursor and OpenAI's like Codex, they earn a lot of money for their code agent, for their coding tools, uh, for serving their code models. But indeed, their code models are quite large. It's like hundreds of million level parameters. And even for the vision generating model, it's relatively smaller, but for using it to generate vision samples like an image, like a video, we need to run the vision models for multiple times. So the computational cost is still a lot. But based on the success of those two kind of models, we are curious. The AI model are growing larger and larger. Is those two examples are just two edge cases, or is a general trend from a scientific perspective, right? It's just some coincidence that their two model are so big, so it's so powerful, or it's a scientifically general trend. And the answer is it is a general trend. And recently, some researchers have proposed the scaling law is actually the first author of the author who proposed the scaling law is the founder of Anthropic. Like in 10 years ago, he proposed that we have the scaling law. And the scaling law is saying that model scaling can bring quality and capability for basically all the AI models. Here is an example demonstration about what is scaling law. Actually, in like 30 or 40 years ago, we already have some language models, but it's only have hundreds of parameters, and it's powered by some statistical machine learning algorithms. So it's the capability of the 40 years ago language model is not good. It can only serve as some specific task helper, to do the n-gram, word clustering, those kind of tasks. But in 10 years ago, a decade ago, we have the deep learning based language model. Those language model have millions of parameters, right? So it can serve as some task agnostic feature learner. It can get the word embedding in our corpus. Right. And within recent maybe 5 years, and everybody knows this part of the story, right? We have the transformer, right? Transformer is in 2017, 18-ish, and Google proposed the transformer. The paper's name is "Attention is All You Need," and everybody in the author list of the attention is all you need becomes very famous and becomes billionaire. But it's opens the era of our large scale models. And nowadays, our large language models have hundreds of billions parameters, right? Basically, it can solve any, you can imagine any kind of language related tasks. Our large language model can solve it. Right. So this is like the one demonstration about what is scaling law. And in essence, the scaling law is saying that model scaling can bring quality and capability, but as the coin has two sides, like what's the bad consequences of those scheme law? From some researchers' perspective, the bad consequences is from the like a computing side. Let's like first review what's AI supply and demand of computing. Basically, for serving those large-scale models, those models with billions or hundreds of billions parameters, we need to have enough memory and computational resources, right? For example, the OpenAI, the Anthropic, those big companies like Gemini, demand, they directly build several cluster center, like a computational cluster centers, right? Each cluster center have like billions of dollars, like GPUs, right, to supply the computational resources. And another thing is that those computational cluster centers cause lots of power consumption, right? For example, I I recently like read the news that OpenAI said the CEO of OpenAI is saying that we are lacking electricity, so they directly bought some power firms to get the electricity exclusively for their GPT models. But it is not friendly to resource constrained environments, right? For example, if we want to run the large language model safely on our mobile devices, we need to run it on our mobile devices, right? We do not want to upload our conversation to the cloud, right? So we need to run the large scale models on some embedded system, right? And another thing is, for example, for the autonomous cars, self-driving system, we need to realize like those autonomous driving system as fast as like real time as possible, right? To avoid some latency, right? But those cars like do not have so many computational resources, right? So we see that there's a big gap between AI supply and demand, especially considering the computation. So like our research goal is to make the AI model more and more efficient. Basically, like our technical research goal is to get lightweighted AI models to reduce the size of neural network or accelerate the inference of the neural network, but without losing any performance, right? So our like I have analogy is like we have our nowadays a large scale AI model is like this very cumbersome, heavy anti-hoc airman suit, but eventually we hope to get like compress it to get a smaller size, but still very powerful, like a Mach 42 size airman suit, right? And our practical goal is to try the AI models from huge computational demands. Like I said, like in 3 years ago, those large language model can only be served on the cluster centers. Each node in the cluster center is like millions of United States dollars, right? And nowadays, I don't know, have you say the news at CES, the NVIDIA released their most state-of-art GPU node. I think it's like three tons of weight of their GPU node. Each node is like several million United States dollars, so it's very costly. I think within recent years of efficient AI improvement, at least some model can be deployed on some customer use GPUs, right? For example, right now we can download the like Ollama application on our MacBook, on our like PCs to run some smaller models, like maybe 32 billion model. It can be run on our mobile devices, right? I think those like a customer used GPUs or like MacBook is only like thousands of bucks, right? I hope eventually we can run those model on some edge devices, on some like small devices. Maybe those devices only like maybe hundreds or within $100. So basically, we want to make AI more and more accessible by lowering AI's deployment costs. So I have a strong suggestion to take this course because like if you want to earn some money and like or impact the stock price of NVIDIA, so you should take this course and do something. So basically, we hope to democratizing AI technology, unlocking the power of artificial intelligence for all the people in the world. And I need to switch to another slides with more details. Basic, basically, I will talk three state-of-art models, three solutions for making two state-of-art model more efficient. First of all, I will talk about our exploration on accelerating the vision generating model, which is the diffusion model. And then I will talk about our exploration on making the large language model and multimodality large language model more efficient. Third of all, we will go deeper about those neural network compression algorithm series to explore why those algorithms can work on the neural network, like to unlock or unveil the black box system in the neural network. Okay, first of all, let's get into the first topic, accelerating the vision generating models. It covered two of my recent work. The first one is the CVPR 2023 work. The second one is Neuris 2024 work. Is like all those work are trying to pushing the boundary of the efficiency of the efficiency of vision generating models. And 1.5 years ago, this demo, this video goes viral on the internet, right? Surprisingly, it's not like it goes viral because it's not shooted by human beings using their camera standing on some Japanese street to take those videos. But it's surprising because it's generated by some video generating models. The OpenAI Sora model. I think last year there's a very popular app, the Sora 2 app. Like everybody is trying to use the Sora 2 app to generating like the Hawking is like jumping from some mountain or those very funny videos. But at the beginning, like before those Sora 2 models, this model is the OpenAI's vision generating model. Like everybody, at least every researcher in vision generative domain is very surprised by the quality of those models. So behind those cool demos, the foundation model is so-called the diffuser model, right? So how many people knows what is diffuser model? Okay, cool. Let's briefly review what is diffuser model. Basically, diffuser model have two process. The first process is the diffusion process. It's also the training process of the diffuser model. Basically, given a set of clean image, we gradually add some noise to the clean image, some Gaussian noise to the clean image, and we use the noise adding step for maybe thousands times. We can eventually transfer the clean image into a total noise, right? And during the noise adding step, we introduce a neural network to estimate which kind of noise was added. Let me admit this student too. We introduce a new network as noise estimation network to estimate in this step which noise was added, right? And this is the training process of the noise estimation neural network, right? After we get the well-trained noise estimation network, we can do the second process, the denoising process, right? Given a total noise, a random noise to the well-trained noise estimation network, we can gradually remove some noise from the total noise, right? And we run those denoising steps also for maybe thousand steps. We can eventually transfer a total noise to a clean image. This is the generation process of the diffuser model, right? Also the inference process of the diffuser model. Definitely based on the demos and there are so many mathematical formulation and proof of the diffuser model from different perspectives, no matter from like a physics perspective or some SD, ODE perspective, they have beautiful mathematical guarantee for the diffuser model. We can see that definitely it's very powerful and revolutionary. But what's the limitation about diffuser model? To answer that, we first need to think what makes a good generative model. In my opinion, a good generative model need to have three qualities. It need to require three requirements. First of all, the sampling the sampling diversity need to be high, right? We generate 1,000 or 10,000 samples. Like we do not want all the samples are similar, right? Second of all, we need the generated samples to be in high quality, right? Like we hope the generated samples should like be high resolution, high instruction following. All the quality should like all those characteristics can be considered as high quality. The third thing is that we need the sampling process should be fast. Right? We cannot use like millions of dollars or like tens of hours to generate just one image. It's not very like it's not acceptable for a good generative model, right? So we call those three requirements as generative learning trilemma, and definitely based on the demo, and we can say that the diffuser model can satisfy the first two requirements. Indeed it can generate very diverse samples, and those diverse samples are in high quality. What is missing is that it cannot do fast sampling. As we reviewed before, to generate just one vision samples, we need to infer the noise estimation network for like thousands of times, right? So it cannot do fast sampling. So our goal to make the good generating model is to make the diffusion model a good generating model, we need to make it faster to accelerate it. In diffusion model was proposed in 4 or 5 years ago. In 3 years ago, there's some work trying to reduce the time step to accelerate the diffusion model. So what is like a high level idea or time step reduction? Is like we have talks mentioned before for generating one vision samples, we need to infer the noise estimation network for thousands time step. Each time step, in essence, in mathematical formation, is to estimate the noise's distribution, right? So the researcher proposed that if we can estimate the distribution more smartly, we can it requires us to infer to generate the image with lesser time step. In this way, we can accelerating the diffusion model's inference. But we argue that there are two orthogonal factors affect the efficiency of diffusion models inference. First of all, is that definitely the lengthy time step. It requires thousands time steps. And the second factor is the larger model size. As we take the example before, for generating one image, we need the model have 7 billion parameters, and we need to run the 7 billion parameters model for hundreds or thousands of times, right? So previous work, they solved the lengthy time step problem. Recently, our algorithms, our diffusion model, compared with 5 years ago's diffusion model, within recent 2 years, our diffusion model only needs like a 10-ish around 10-ish time step to it's okay to generate one vision samples. But we argue that what is missing is the model size, the noise estimation network still very large. So we propose that the neural network in the diffusion model should be comprised. So we to solve this problem, to comprise the noise estimation network in the diffusion model, we first need to review the general pipeline of traditional network compression method. Basically, for the traditional neural network compression algorithms, it requires the pre-trained model, like the ResNet model, right? And we need to choose the network compression algorithms, like knowledge distillation, like factorization, like quantization, like pruning, there are different neural network compression algorithms, right? And after we get the compressed method, we need to access to the full training data of the original neural network, right? Like the ImageNet, MS Coco, those very
Depends on the network compression type, or it is like I can use any type of network compression to do.
You can use any network compression techniques to do this. It's a general pipeline for the traditional network compression methods. So after we get the training data and the compressed model, we need to retrain or fine-tune the compressed model, right? And then we get the a well-performed compressed model. This whole pipeline, this whole paradigm called compression aware training. And all the in several years, in 5 years ago, all the network compression method can be considered as compression aware training, like quantization, pruning, knowledge distillation, all the methods. But those traditional method does not works for the compressing the diffuser model, basically for two reasons. First reason is that the training data in diffuser model is inaccessible. Why is inaccessible? From the academia people's guess is that those big company, even they release their diffuser model, the checkpoint, the pre-trained checkpoint for their diffuser model, but none of those companies have released their training data, right? The hypothesis is that their training data contains some sensitive data. So they it's 100% sure that they cannot release their training data, right? And the second reason for why the traditional method does not work is that the retraining and fine-tuning is impractical for diffuser model. Because as we mentioned, training those large-scale models cost millions or tens of millions, GPU hours. It also costs millions of dollars. So it's empirical to retrain the whole diffuser model. So we propose that the training-free concept is very important for compressing the diffuser model. But how to realize this idea in a training-free manner? Our solution is some post-training quantization method for the diffuser model. Basically, we only need to get access to the pre-trained model, and we do not need to get access to the training data. And to get access to the pre-trained model is okay, right? Many companies have released their checkpoint, pre-trained checkpoint. We can download from a stable diffusion, some flux. They all release their pre-trained checkpoint, and we do not need to get access to their training data. We only need to get access to some a very small amount of calibration data is okay. I mean the very small amount means very small. It's like a 0.01% of their training data is okay. And because the diffuser model is a generative model, right? So we can use the checkpoint, use the pre-trained checkpoint to generate some image as the calibration data. So the calibration data is easy to access. And instead of using to fine-tune or retraining the whole compressed model, we only need to run some algorithm to calibrate and quantize the pre-trained model. We can get the well-performed quantized diffuser model as more efficient to run those diffuser models. So basically, this whole post-training quantization solution is totally training-free.
So in this case, what would be the difference between the fine-tuning and calibration? I understand fine-tuning usually you would adjust the weights of the different things you're looking at.
Yes.
What would it look like in calibration?
Oh yeah, I will cover this calibration part a little bit later. but like high levelly, like fine tuning is trying to fine tune every parameters, every weight parameters in the large scale neural network, right? But calibration is like uh to collaborate a very small amount of like hyperparameters in the neural network is okay.
Instead of all.
Yes, yes. To choose a couple of we will cover this a little bit later. After it get quantized. So you have a question? Yeah, after we get the quantized diffusion model, why the quantized version is more efficient is that if we can quantize the weight parameters and the activation parameters in the neural network into some low position, we can replace the 4-position matrix multiplication into some low position matrix multiplication. This low position matrix multiplication is more efficient, right? So I think like I assume you already have some deep learning and machine learning background, and you must know that the matrix multiplication is a major computational consumption in our nowadays deep neural network, right? So if we can replace the matrix multiplication with some low position operation, it will be very efficient for the neural network. So how like this like slides answers what's the difference between fine tuning and calibration? Like exactly this equation answers that question. Basically, we do not need to fine tune all the parameters. We only forget the quantized weight matrix or the activation matrix. We only need to have two hyperparameters like this scaling factor and this 0 point. Those statistical like factors we can quantize the whole a weight matrix or the activation matrix into some low position matrix, right? And this scaling factor and 0 point is compared with the whole parameters is like a very small amount of hyperparameters, right? And the quantization equation is quite straightforward. Basically, we do some clap and run to nearest operation. We can quantize those matrix into low position matrix, right? But actually, for quantizing the weight matrix is more easy, right? Because we just load the pre-trained diffusion model to the GPU, and we can get the weight matrix like straightforwardly. And the weight matrix is fixed, right? It's loaded from the checkpoint. So, and for getting the scaling factor and the 0 point for fixed matrix is easy, right? But our activation matrix is dynamic, right? It depends on what's the input and what's the weight matrix is. So it's hard to get the quantization parameters, those scaling factor and the 0 point in the activation matrix, right? The most major reason is that those activation or the feature maps are not static. It depends on the input and the weight matrix. So our challenge is how to get the activations quantization parameter. To solve this problem, we do some explorations, and our major observation is that the distribution of here the x-axis of the figures is the distribution as a range of the pyramids of the numbers in the activations, and the y-axis is accumulated numbers in the activation matrix. We can, based on those figures, we can find that the distribution of activation changes dramatically with time step, right? And here you can see that the purple one is the time step near the clean image, and the gray one is the distribution of the activation near the noisy side. So we can see that there's big differences. So we propose that we should collect a small number of noisy image to do the calibration for the activation quantization. So it goes to our method PPQ, post-training quantization for diffusion model. Basically, our algorithm has three steps. First step is that we sample some distributions following this normal distribution, like this normal distribution. We sample some time step Ti following this skewed normal distribution. Second one, we feed those collected time step Ti to the pre-trained pre-trained diffusion model. We can sample some XTI. This is the image with different noisy levels, right? And after we get the XTI, we can get our collaboration size C, and we feed those collaboration sites C to our quantized diffusion model as a calibration. We can collect the scaling factor and the 0 point for the activation matrix, right? Here's some experimental results of our method. The IS score and FID and SFID is the metric to measure how good our generating models is. Basically, the higher IS score is better, and the lower IS score is better. We can see compared with the 4-position diffusion model, our the performance is in the same level, but because we quantize our diffusion model into 8 bits, so we can replace the 32 bits matrix multiplication with some 8 bits matrix multiplication. So we can speed up the diffusion model 4 times while maintaining comparable performance. Here's some qualitative result. Compared with the 4-position diffusion model, our quantized model's performance is comparable. And also we have seen that there are some different paradigm for accelerating the diffusion model is to reduce the time step, right? Our method can serve as a plug-play module, like orthogonal to those time step reduction method. Like in total, we can accelerating the diffusion model around 100 times. And we would like to highlight that our work is the first work on accelerating the diffusion model's noise estimation network. And within recent 1 years, the world model comes, right? And behind those world model, so-called world model, is the diffusion transformer. They replace the deep neural network, like a convolutional neural network with some transformer architecture. So our question is does our solution, those post-training quantization solutions, still works on the world model, on the diffusion transformer? Our answer is yes. like in last year's, like in Europe's 2024, we have this PTQ, those following up work, PTQ for DIT work. We found that it still works. Our PTQ, post-training quantization solution, still works on diffusion model. Here's some like result of our PTQ for DIT on those high resolution and video generation diffusion models. Our PTQ for DIT still works. It can accelerating the diffusion transformer for like also for 4 times without losing any performance. Okay, let's get into the second chapter. Do you have any question about the first? Yeah.
Inference is like 4 times faster.
Yes. Yeah, it's like 4 times faster. Theoretically, if you do the A-based quantization, you can get around 8 times acceleration, but like it need you to do some very deep optimization for your whole system. Like you need to write some CUDA kernels to get the fully usage of your GPU. But like 4 times is pretty accessible. So our next research topic is efficient large language models. It covers our research on if activation aware SVD for compressing the large language model. Basically, at that time, we have 3 paradigms for large language model compression. So we propose a new paradigm. Basically, in 2 years ago, we have like a 3 paradigm for compressing large language model. We have the pruning paradigm, like can prune some parameters from the large language model to get a smaller size one, and we can definitely quantize the large language model, right? And the third paradigm is noise distillation. We can distillate to get smaller size models. So our research question is there new possible paradigm for large language model compression? Our answer is yes, there is a new paradigm, which is low rank decomposition, or it can be also called like low rank factorization, right? Basically, the idea is that given a very large size weight matrix W, if we can do some SVD and truncation techniques, we can decompose those very large weight matrix into 2 matrices, those left singular matrix U and right singular matrix V, and singular value vector sigma, right? Basically, if the K is smaller enough, the SVD can compress the weight matrix, right? But we empirically find that those naive approach fails in large language model. So what's the challenge of implementing those SVD in compressing large language model? We basically found that there are 2 challenges. First of all is the influence of the activation of layers. And the second challenge is the sensitivity of SVD varies among different layers. So let's tackle those 2 challenges one by one. The first one, the activation of layer, the activation of layer one. So let's first take a look at what's the activation of layer phenomena. Basically, if we here is one example. If we visualize the distribution of the in the activation matrix, we can see that the x-axis is the index of the activation matrix. The row number, the row index of the activation matrix. and the y-axis is the column index of the activation matrix. And the z-axis is the value of each element in the activation matrix, right? We can see that some all-layer values distribute channel-wisely in the large language models activation matrix, right? We have three very high outstanding like a column distributed in the activation matrix, right? And another thing is that this activation all layer phenomena is not unique, as almost every layers and almost every large language models have those issues. Like this paper do a very a comprehensive study of this phenomenon, and basically we can find that those channel-wise all layer is everywhere in the large language models. So why this phenomena affect the effectiveness of using SVD to compressing the large language model? How do activation all layers make the SVD fails in LLM decomposition? Here is our I have this demonstration to show why this happens. Basically, if we do the weight matrix decomposition using SVD, we can also reconstruct it back to after we get the decomposed matrices, we can reconstruction back to the four sides matrix, right? But those reconstructed matrix have lower precision, so we can compute the reconstruct the matrix error, those delta W, right? If the input activation have some odd layers like this X matrix have some odd layers. Basically, even though our reconstruction loss delta W is very smaller, the output error can still be very huge. Like this, even the delta W is smaller, but the delta Y can be still very huge. Because of the input activation all layers are not considered, right? We have, for example, if this channel is the all layer channel, even though the reconstruction matrix error is smaller, but the output error is very huge. So we propose that those activations should be considered during the LM decomposition. But next question is how to consider it. Our solution is the ASVD, activation aware SVD. Basically, our whole high level idea is that if we find this channel is channel in the activation matrix is the all layer channel, we can correspondingly scaling the weight matrix like this weight matrix, this channel, right? And it can help us to minimize the output error, right? It can minimize the output error delta Y, right? This is just one demonstration. More technically, how can we scaling the weight matrix? Here, the W is our targeted matrix. This is the matrix in the large language model, right? If we can introduce some diagonal scaling matrix, this S is constructed to represent the impact of input channels on the weights, right? We can do the decomposition on WS instead of W, right? And because this WS is scaling, some channel is scaling, so it's easy to be decompose this. It will minimize the output error, right? And because the S is a diagonal matrix, so the inverse of S is also a diagonal matrix. So the the inversion of the S is easy to compute, and the whole matrix multiplication is also easy to compute, right? And more specifically, how can we design every element in the diagonal matrix S is that we channel-wise, we calculate the channel-wise average in the activation matrix S X. Our second challenge is that the singular values variation among different layers. We have do the visualization here. The x-axis is the decomposition ratio of the decomposition algorithms, and the y-axis is the perplexity of the decomposition large language model. Basically, the lower means better performance of the decomposition large language model. We can see that different layers have different sensitivity to the decomposition, right? So have anybody have some? Yeah, go ahead. This one?
Oh, previous one. So you showed a figure where there were jumps in the input activation.
Mm-hmm.
So could you like explain what those jumps signify? Like why do we have those jumps in the internet?
You mean why the all layer?
Why we have minus 22.9 minus 35.5?
Oh, you mean why this like all layer phenomena happens, right? Actually, like in nowadays, the researchers have not have a common agreement why this happens, but what we agreed on is that this phenomena does exist. Like this all layer phenomena is an issue, but the researchers still not get a very clear understanding why it happens. Yeah, go ahead.
Is this specific to the transformer architecture?
It's not specific to transformer architecture. It's specific to large-scale transformer architecture. Only the transformer like more than several billion, it will have this issue.
So for the first token, I have heard about like something called attention sinks that
Oh yeah, attention sink. Yes.
all this to happen. I don't understand why there is like the 200 like like after that, after the first one.
Yeah. So our second challenge is that the single value varies among different layers. To tackle this challenge, we propose the sensitivity truncation rank searching algorithms. Basically, we also collect. Yeah, go ahead.
Yeah, so for the weight scaling you were talking about, is that just to address the activation like bias? Reduce your weights in that.
Yes. Basically, if we find, for example, if we find the second row is scaling, is the all layer in the activation matrix, we correspondingly scaling up or down of the second column in the weight matrix, and the S is designed to do so. And basically, for getting the optimal rank for different layers, we run we first collect like several sentences as our calibration sentence. and we run the binary search algorithms to find the optimal rank for different layers, different kind of layers. And this is our ASVD algorithms. Basically, we have it have two benefits of the ASVD algorithms. First of all, is as we mentioned at 2 or 3 years ago, they only have three paradigm like pruning, quantization, and noise distillation. And our decomposition algorithm is orthogonal to those LM compression paradigms, right? We can say that by combining our decomposition algorithms with some quantization algorithms, we can further improve the performance of the compressed method to make it more efficient, but maintaining its performance. The second benefit is that we can compress the KV cache in large language models. So like before we get into this, I have a question. How many people have background in transformer in large language models? Okay, maybe we need to also talk briefly about maybe like in the future we will talk about some background in transformer and large language models. And those KV cache is not for nowadays large language model. KV cache is a major efficiency bottleneck in large language models. Basically, our nowadays large language model can realize very long sequence understanding, right? It's not like 2 years ago, our language model will forgot what you told him like 1 hour ago. Nowadays, our large language model can understand the whole content like without any forgetting, right? Basically, this is thanks to the KV cache, but also because our sequence, our conversation with the large language model becomes longer and longer, right? So the KV cache becomes the major efficiency bottleneck. Basically those the KV cache is stored in a L times N size of matrix stored in the memory in the GPUs, right? If the length of the content L is very large, this storing this KV cache matrix is very costly, right? So our solution, by using our solution, because we decompose the weight matrix into 2 low rank matrix, right? So we can store L times R size matrix in the memory. We do not need to store the L times N size of matrix. Right? So basically our method empirically, our method can like save the KV cache 4 to 10 times without losing any performance. And basically like the high level idea of making the KV cache low rank is also used by some by the DeepSeek papers. Is like this DeepSeek paper is in 2024 and our paper is in 2023. It's like a half year earlier than this DeepSeek papers. They also use the concept of low rank for saving the KV cache. Okay, I think the time is close to end.
2 minutes left.
You
have about 2 minutes left.
Yeah. So basically, I will leave the zero part to next class and see you on Wednesday.
When are you planning to post the academic application?
The activity, I will upload it today. So basically, a small quiz with no, with some relevant question is enough, right?
Yeah, you can just say, have you read the syllabus and please check yes or no.
Okay, got it.
That's no.
Okay, thank you. Let's
Considering after and tourism, like we're like right now like to like try to apply for like volunteer.
Oh, cool. Yeah, that's very cool. I also have some research about like
I have some